averaging over the extra dimension. So there was the notion that the extra dimension was small and nothing depended on it. Yesterday, when we looked at the stability issues well, in the case of the Kaluza-Klein black string in detail, but it illustrated a more general problem with extended horizons, that if they got too long relative to their width, then they have a tendency to start to ripple. So the end point of that process is not for sure known, but we suspect that the horizon actually splits to form an array of black holes, rather sort of backed up by that numerical simulation I was telling you about, in which case we get a sort of instantaneous naked singularity. So it's kind of an interesting story, but the instability occurred with a sort of Fourier mode along the length of the extra dimension. So I was saying that corresponded to a massive state from our four-dimensional perspective. Now, with a warp compactification, it's almost like the complement of Kaluza-Klein. Instead of having something that doesn't depend on the extra dimension, quite often we see in a warped compactification that not only does the geometry depend very strongly on the extra dimension, sometimes that can be the dominant feature of the geometry. So I'm going to give a concrete illustration of a warped compactification, which is about the simplest example you can get, a toy model, which was put forward by Randall and Sudrum in 1999. So that uses anti-de Sitter space and these domain walls that we've already seen. So we've got all the tools kind of in our kit to analyze that particular model. So that's what we'll do concretely. But what Randall Sudrum illustrates is this principle of having a geometry that very strongly gets squashed as you move away from a particular location. It also uses some idea which is either localization or confinement. So it introduces an idea of a brane or a brane world that maybe we live on some hypersurface in a higher dimensional manifold. So these are all ideas that this toy model kind of encapsulates. But the features of having metrics that kind of strongly deform into the extra dimensions, those tend to be used in some modern ideas of compactification in string theory, where you stabilize some of these degrees of freedom, these scalars that we saw when we did the Kaluza-Klein reduction. So the motivation, actually, or why Randall and Sudrum originally did this, remember when we did the Kaluza-Klein theory, I sort of made a point of saying that there was a renormalization or a rescaling of Newton's constant. And I could rephrase that the four-dimensional Planck mass is related to the five-dimensional Planck mass by a factor of the size of the internal direction. And so what this is doing is it's giving a change in the Planck scale. So if I were to imagine just a rather generic picture, if I have general d space-time dimensions, then I would get my four-dimensional Planck mass by taking the higher dimensional Planck mass and multiplying by a volume factor of the extra dimensions. So if I'm in d dimensions, I've got d minus 4, which I could also call n extra dimensions. So this is just a very generic, at the moment I'm not fleshing it out, I'm not giving it any justification, I'm just saying let's just look at orders of magnitude. In this case, I could say, well, let me invert that and find the scale of the compactification. And so I can write that. So normally, in original Kaluza-Klein theory, we would have been compactifying sort of at the Planck scale. In other words, the length scale would have been the inverse Planck mass. And so these two would have been essentially the same. But you see that if we say we want to have something which is a sort of larger scale, then we actually start to lower the higher dimensional Planck mass. So we can quantify that. So we've got here something like so this is the sort of scale that we're talking about. We can compactify on a scale which is, sort of units that we're familiar with, or at least something that we can kind of relate to. And we can potentially bring this higher dimensional Planck scale at the moment. We know that we can bring it down to something like, well, not 1 TeV, but let's say 10 or 15 TeV, at least as far as direct experiment is concerned. So, for example, if we had 6 extra dimensions, we could get this compactification scale to be incredibly small from a R perspective. It's obviously not small from a particle physics perspective, but from a gravitational perspective, we don't have a hope of probing that sort of scale. So So that's the sort of statement that gravitationally we can't rule this out. So all we would need to do would be to find a mechanism such that the standard model couldn't probe those extra dimensions, and then we wouldn't know, okay? And then what would we have done? Well, what we would have done would have been to lower our scale of new physics, which, is sort of up either at grand unified scale or up at the Planck scale, and we've kind of lowered this new physics scale down to very close to the standard model scale. So one of the problems that we have in the standard model is that this hierarchy problem, as it's called, the fact that there's this huge desert of sort of right up to a very high energy scale, and how do we actually stop stop all our coupling constants from running? So typically supersymmetry has been invoked to actually make this work, but of course, so far, that has not been seen. So it's a bit of a slightly crazy idea, this geometric resolution of a hierarchy problem, but nonetheless, crazy or no, you usually have to take into account any alternative when you're looking for new physics that you're not exactly sure what it is. So this is sort of, it's by no means, a favored solution to the hierarchy problem. It's just simply one that's been put forward, so we kind of have to investigate what does it say. And so our geometric picture So the picture is that gravity is kind of spreading out into the extra dimensions, and so is weakened. So if we had our cylinder, which is of course not a brilliant example because it doesn't really, give us much spreading out of gravity, but if we had some source, you could imagine if you just wanted to draw kind of lines of force, that, these lines of force would kind of spread out on the cylinder. And although when you go far, if you sort of pan back enough that you don't see the extra dimension, you still see something that looks four-dimensional, it's still weakened because gravity's kind of spread out over the extra dimension, and the factor by which it's weakened is sort of the size of the extra dimension. It's just a qualitative picture, really, to kind of give some intuition about, about what's going on. So the real key here is that we have to make sure that only gravity or some very small number of fields, which reduce just to gravity at our scale, can probe the extra dimensions. Yeah, sorry, just hang on. Yes?
Yeah, I'm not very clear about what you mean by saying that we need to ensure only gravity sees extra dimensions.
So, in other words, if we had say if the Higgs boson could see the extra dimensions, then that would mean that we would, because of the scale of the extra dimensions, which is ludicrously, much bigger than scales that we're probing at LHC, then we would have expected to see this in standard particle physics, not just at LHC, in every interaction pretty much that goes on. So our standard model really does seem to, works in four space-time dimensions, et cetera, et cetera. So it's not seeing this extra dimension. So that's really what I'm kind of saying. And so what I'm going to do is to give a sort of heuristic motivation. And it's actually quite a nice idea that was around long before Randall and Sudrum put forward their particular model, for almost about 20 years, actually. So we're going to go back to our domain wall, and we're going to look at a process which is called a sort of condensation, and just sort of use that as a motivation. Now, I could just say, well, in string theory, we have objects which are kind of lower dimensional, dynamical, and which carry gauge fields, which are the d-branes. Open strings can end on d-branes, and the end points of open strings carry charges. If you're happy with that, that's fine. On the other hand, that's not, I don't think you've done that particular course yet, so let's actually work with some of the physics that we've been exploring to see that this idea of localization or confinement is actually quite generic in physics, not just string theory. So it's something that we do actually see in other systems. So we derived a solution to a scalar field theory which had a potential with two separate minima. And so this is a non-perturbative solution, and it's sort of a legitimate non-trivial vacuum around which you could quantize. So now I'm going to couple this system. So we're all really talking here about sort of effective descriptions, but anyway. So I'm going to couple this to a fermion, and I guess I'm going to sort of hop up into 5 dimensions. It doesn't change the arguments that we had. There we go. So let's imagine that we introduce a fermion field which couples to our scalar. Now, normally, if we were in a vacuum, this scalar would give us a mass term for the fermion. But we're not quite in a simple vacuum, we're in this profile. So what it means is that we've got a sort of position-dependent mass term, but around the middle of the wall, phi is sort of roughly 0. So it means that our fermion looks like it's massless. So it's sort of not obvious what might happen. And given that I've written down a sort of background solution, which is stable and non-trivial, I could say, is there a background profile here which is also stable or non-trivial? So that's the sort of question. So then I have to look at this equation of motion in the background. This is what it reduces to. This is my profile. And what I sort of notice is if I, yep.
So you said we're in 5 dimensions, so the wall is a 3-brane?
So yes, but it's still the Tanch profile, yeah. So, I mean, I'm not thinking about gravity at the moment here at all. I'm just talking about from the perspective of the kink solution. And so this gamma 5 really is, the 5th gamma. So, but it's the same gamma 5. So this is what we get, and you can see if Tanch were 1, then that would be a sort of more conventional mass term. So normally, if you differentiate such, you get such Tanch. And so if I pick this particular value or profile of psi, then I get a solution that looks like this, provided I have a particular property of my psi naught. So psi naught has to be chiral. So now I could imagine, so what I've got here is, here's my domain wall profile, and I've got something that looks, let's just say, looks something like this. So what I've done is I've found a way in a non-trivial background. I've seen that the fermions also develop non-trivial profiles. This is actually the lowest energy configuration for psi in that background. So this is called a condensate. And the idea is, your fermion would normally have a sort of standard vacuum, pop in the domain wall, and suddenly it wants to condense. It wants to sort of develop this non-trivial profile localized around the wall. So now we can say, well, what are the lowest energy excitations? Well, I could imagine taking this psi naught and making it position dependent, and as long as I keep make sure it behaves like a massless mode in 4 dimensions, then that's also, at least at low energies, a solution of the equations of motion. And so what I've got now, the wall itself looks lower dimensional. So we start in 5 space-time dimensions. The wall looks like it's a 4-dimensional space-time. We've got this condensate, which again has a profile in 5 dimension, the 5th dimension. But the excitations of the condensate look like something 4-dimensional. And so what we've got is 4-dimensional physics from a 5-dimensional theory. And so this was an idea put forward, as I say, in the early 80s by Rubakov and Shaposhnikov. I think the paper's called something like, is our universe a domain wall, or do we live on a domain wall, or something to that effect. But it's actually just a really nice idea and somewhat ahead of its time. This notion, of taking things that people knew about, condensate, zero modes, etc., and applying it to some slightly crazy picture with extra dimensions.
So does the masslessness follow from the chirality?
No, the chirality is so that you get this profile. You need that to get this profile. This is only a solution. It's not a solution for all the degrees of freedom sitting in psi. It's only a solution if you've got this constraint here. And then the 4D, the sort of massless bit is just, well, what's left of this equation once you've pulled out that profile? So that's an alternative way of trying to motivate confinement. Obviously, it's got its limitations in the context of this particular theory. You can see that if you sort of heat the system up or make it energetic enough, you're going to move off the wall. But at least it gives some justification to this notion that perhaps we could have a lower dimensional object on which our physics, our standard model, propagates. But of course, gravity, being geometry, always sees every dimension that's there. So that's kind of the picture. So let me introduce the toy model, and then we'll discuss it. So with Randall Sudrum, it's constructed out of, it's a sort of domain wall in anti-de Sitter space, so 5-dimensional anti-de Sitter space, so it's a 4-dimensional universe. And the metric is strongly warped. Away from the wall. So our picture here, this is what we're going to sort of try to describe, is that there's a domain wall. Our anti-de Sitter space if you see the way I've written it, this is four-dimensional flat space. So here is our wall, and eta mu mu. And so the only dependence of this metric is the fifth dimension. So we've got this notion of our wall kind of being squashed as we move out. So our transverse directions are squashed exponentially as we move away. So let's see how we describe this picture gravitationally, because if we are going to discuss warp compactifications, we need to do it fully consistently within the context of Einstein gravity. So rather like we did in the Kaluza-Klein theory, where we reduced a five-dimensional gravitational action to 4D, we're not going to do that, quite so explicitly here, but we are going to solve five-dimensional gravity. So here are two terms in the gravitational action. We've got what we now call a bulk term, which is the 5 higher dimensional manifold. And this we could call our brane term, which is the lower dimensional manifold. So in the notation that we did with Gauss-Kodazzi, it would be M and sigma. So these are just some terms that we use, bulk and brane. And when we derived the Gibbons-Hawking term, we varied the boundary term, but at that point we were assuming that H was constant, was held fixed on the boundary, because we were doing like Euler-Lagrange. So if we do a variation, but now allow a variation of the metric on the boundary, then if you look at our notes, we actually derived this particular, this was back in lecture 7, we derived this particular expression. So there were also the terms that cancelled off the boundary pieces coming from integration by parts, and this was what was left. This was another piece that we got. And so if we view our wall, so if I focus in on my wall, let's say this is my wall. So I imagine it it should have finite thickness, but I'm going to try and describe it with 0 thickness. So here's M plus, my bulk, and M minus on each side. And this would be the two normals, N plus and N minus. So, and then I let the wall thickness go to 0, and that's what I'm left with. So this is what I should expect to get. So sigma here, this is my brane world. Sigma is going to be sourced by energy momentum. So I've got this notion that my energy momentum tensor is going to have a delta function on that surface. Now, that's a little bit of an assumption. In this case, the reason I'm going through this route is because what we're deriving is a set of equations which tell us how the extrinsic curvature relates to the energy momentum. Those equations are called the Israel equations, and they were derived in the 60s by Werner Israel, who was thinking about problems in astrophysics and imagining modeling gravitational collapse problems by looking at shells of dust. And so he needed to know whether or not you could take a Dirac delta distribution if you were dealing with general relativity. And he showed that you could. And so, so therefore this is okay to do, setting this delta function. So, but I'm just pointing out, I haven't really shown that you can. So now if I take this boundary prescription, so what I mean by those angle brackets there is really just I'm taking the extrinsic curvature on each side. And so here are my boundary terms. You can see that if this is m plus and n plus, I've got KAB minus KHAB on the plus side, and on the minus side, the h's have to be the same. And then in my full action, I would also have energy momentum, something sourcing the energy momentum. And so my Einstein equations for the full action are composed of a bulk set of Einstein equations plus these brane or boundary Einstein equations, where the terms coming from Gibbons-Hawking on the boundary have to match up with any terms coming from brane energy momentum. And so this is what I get. And these are actually the Israel equations. Now, what Israel actually did Israel actually took the Einstein equations, projected them via a Gauss-Codazzi prescription that we've done, sort of into parallel and perpendicular components, and then took a limit as that width went to 0. So you can see that there's a convention. This is sort of, as you're well aware, conventions can be a bit of the bane of our calculational existence. But notice that this n minus points in the other direction. So typically, when you see the Israel equations, what you actually see is delta KAB minus delta K, HAB is 8 pi G, SAB. It's the same thing, it's just the normals that are different. The notion is you're taking the difference, the jump in the extrinsic curvature, and that is telling you about the stress energy of the source, the wall. So here, obviously, the sign of the normal is continuous, okay? So with Randall Sudrum, our wall, if I look at the way I've written anti-de Sitter space, I was careful to only write it for z bigger than 0. So for Randall Sudrum, in this case, what they're doing is they're taking something which is reflection symmetric around z equals 0. And so really all we need to do is to calculate the curvature on one side and multiply by 2, because it's just symmetric. So if I look at n plus, which is z greater than 0, then n plus is d by dz, so that's our outward pointing normal. And so k so my k, remember k is just the covariant derivative of n projected parallel to the surface, to sigma. And of course n d by dz is just the proper distance, or z is the proper distance. So our normal just has a -1 in the z component, so that's why I get this. And so really all I've got is gamma z mu nu, which is a half g mu nu primed, and so that's minus k g mu nu. So that's what my extrinsic curvature is, and so my jump in extrinsic curvature is simply proportional to the metric. If I trace over this, I get that delta k is minus 8k. So at z equals 0, which is where our wall is, so if I look at what S is, well, the Israel equations told me that S was related to the jump in K. The jump in K is proportional to the metric. So if I take KAB minus delta K times H, I've got minus 2 plus 8. So what I end up with is 6K. Eta mu nu, because we're looking at z equals 0. So this is my S mu nu, and so this is proportional to H, and this is precisely what we found for our domain wall energy momentum. But note that the tension of the wall is tuned to lambda. So we can't have any brain energy momentum here. It's got to be a very specific value dependent on the cosmological constant. So that's our Randall Sudrum configuration. So we've shown what we've actually done here in order to show what that the solution is legitimate, is we've also derived the Israel equation. So here I've applied it to a specific example, but these Israel equations hold quite generally for any hypersurface. It doesn't have to have one of these brain energy momentums. So it could have no tension or pressure, for example, which of course was what Israel was doing with clouds of dust. So let's just sort of recap, where are we? We've said that we can localize on a lower dimension from the perspective of particle physics. We've said that we can solve this lower dimensional space consistently within gravity. What we haven't said is this gravitationally consistent? In other words, what is our four-dimensional effective gravity theory? So with Kaluza-Klein theory, we could actually do that very specifically. We found the full spectrum of excitations for a general sort of space-time with a general size of the internal manifold. The only assumption we made was that things did not depend on the extra dimension. Here, we can't actually be quite so general. For a general compactification with a general warping around a general brane, that's kind of a bit of a tall order. But what we can do is we can show that the gravitational theory living on the brane is, at least at low energies, standard Newtonian Einstein gravity. So that's what I'm going to do now. I'm going to kind of track through the steps that Randall and Sudrum took to try and demonstrate to you that gravity on the brane is sensible. So we did this yesterday. We are going to do it via perturbation theory. So we're taking our background Randall Sudrum metric. So this G here is RS, and we're adding a little perturbation. And we're going to say, how does that perturbation behave? Does that look sensible from the perspective of the person living on the brane, the HAB? Yesterday, when we looked at a particular example of solving perturbation equations, I took a transverse trace-free gauge, where the trace of my metric vanished and the divergence vanished. But I commented that gauge was something that you took as a case-by-case basis. So this is part of the reason I've chosen this particular demonstration of 4D gravity, because I'm going to choose a different gauge. So I'm going to choose a gauge that's consistent with the fact that we've got a wall. If we have a hypersurface in any dimensional space-time, I can always define a z coordinate in the way I've done there. Because what I do is I take the normal to my surface, and I just integrate out geodesically, and I define my transverse coordinate to be the length, the distance, proper distance away from the wall. That's going to be a fine coordinate as long as I never go within a radius of curvature. It's certainly always going to work locally. So what that means is that if I take this Randall Sudrum metric over here, and I just, instead of having Minkowski metric there, I say it's some arbitrary metric. I may need to change the warp factor a little bit, but I can still keep dz squared.
This analogous to like a normal coordinates.
Yes. So in fact, it's called Gaussian normal as a gauge. So the gauge is HZA equals 0, and it's called Gaussian normal. So the reason for doing it is simply it mirrors the physical system we've got. Now, what we can do, which I'm not going to demonstrate, is that you can show that the remaining H is transverse trace-free in the bulk. So remember, that means that H lambda lambda is 0, and a grad mu of H mu lambda is also 0. So you have to do a bit of work, but you can show that that is consistent away from the wall. But what that means is that there are two ways, or sort of we can think of two ways to perturb the system. So here's our background system, which is now the nice straight flat wall, perfect ADS. And we can imagine that we go to a wobbly wall with sort of ripples in the bulk. So the wall moves and bulk ripples. I call it ripples, but you know what I mean? It's like gravitational radiation, some perturbation in the bulk. So for our Gaussian normal gauge, we want Gaussian normal, which means we want Z to mean distance from wall. So we need to move our wall back to Z equals 0. So we say that Z goes to Z plus F of X. Okay? So that's all we're doing is, this is our perturbed system. Here we've got an H mu nu transverse trace free. But of course, to get this transverse trace free, my wall may have moved. So what I now have to do is kind of slide my sort of Z slices so that my wall is now flat again. So here we could say our gauge transformation had psi mu, sorry, I think that means psi Z is F, written there. So I'm going to call just because I want to be slightly more general, I'm going to call this warp factor, this deformation factor, A. So in general, yes, I can change gauge. I need to keep things being Gaussian normal, so I have to be careful. This has to be 0. So it means I have to do a change of gauge where my psi mu is F comma mu, which is given in terms of some integral of the warp factor. So I can make my wall flat again. I have to do a gauge transformation. And so I've got now for my full metric, I've got the transverse trace free bit, my full perturbation, sorry. So, yep.
So is this how we're defining the xi z to be f and the other components to be derivatives of f, right?
Yeah, so my psi z is f. That tells me I'm moving my z direction to 0 the wall. If I want to keep, that's fine for gzz, but I need to keep gz mu to 0 too, which means I have to simultaneously do a gauge transformation in the x mu directions. So if I shift my wall in z, I've also got to shift my x, t, x, y, and so on coordinates to keep, to keep the cross term 0. So I have to do, this is the gauge transformation I need to do to return my wall to z equals 0 and keep Gaussian normal. So the reason is, what I'm really doing in here is I'm saying that the actual physical content, or plus some gauge, of course, of my perturbation is something which is transverse trace-free, so obeys the nice Slichnerovich, the simplest one, and something which could have a trace, but this bit is telling me that the wall has actually deformed. So I'm identifying the different parts of my perturbation and giving them an interpretation. So if I'll just quote, it's not too bad a calculation, the Slichnerovich operator, because in the background, because you've got this really nice exact ADS bulk, the Riemann tensor is just given in terms of sort of a constant, the K times different combinations of the metric, similarly Ricci. So it's not too bad a calculation. The worst part of it is kind of the pieces that belong, you know, the divergence of H bar, which you kind of have to keep track of because you know those F terms are sort of hiding in there. So if I look at this Slichnerovich equation, the pieces that matter well, the Z component, we get something that involves the trace of H. I've said that the only thing that H can have a trace of is terms involving F. And then the piece that's directly proportional to F has a factor of A squared in it, so that gives me nothing. And all I'm left with is D squared of F. So that, by Slichnerovich, is equal to the trace of the energy momentum tensor. And then you can see that the cross terms, or you can find out the cross term equations are satisfied. And what you end up with is an equation for HTT. So what I'm assuming here is very much that I've only got perturbed energy momentum on the brane, so hence those delta functions on the right-hand side. And you can see that this is actually not dissimilar to the black string instability equation. We've got something that looks like a four-dimensional Slichnerovich operator, because the four-dimensional space is flat, with a piece that's dependent on the extra dimensions. And so, in fact, in a similar fashion to the black string, we can separate variables. We can just do a sort of standard Fourier decomposition in our space-time directions. We have an eigenfunction, um, in the transverse direction. So remember with, this was e to the I mu z for black string. So here we can't, it's not a simple Fourier mode, but we can imagine we've got some transverse eigenfunction, and we've got some sort of polarization type of tensor telling us about the tensor components of H. So it's really saying that H is a relatively simple, sort of a simple decomposition. So our d squared of H mu nu is just going to be minus m squared of H mu nu, where p squared here is what's identifying our m squared. So the eigenfunctions, we simply sort of use this. The eigenfunctions obviously depend on this value of m, and m we would interpret as a mass of a spin 2. They're usually called Kaluza-Klein graviton. No, of course, this is not Kaluza-Klein theory. It's something which is related to the extra dimension. So we can solve for U by simply putting in the actual values here. You can see that m squared U plus this combination of derivatives has to be 0. So it turns out de Sitter space makes things a bit more complicated than a simple sine wave, but not too bad. It turns a sine wave into a Bessel function. So it's still an oscillatory mode, it's just got different amplitude. That's what does ADS, did I say de Sitter? I think I said de Sitter. That's what ADS does. So this is it looks complicated, but really all you do is you sort of pop in that change of variable, you look at that ordinary differential equation, and you see with the change of variable, lo and behold, it comes out to be a Bessel equation. And so that's where this comes from. The combination of Bessel and Neumann functions comes from the fact that on the wall you have to have this very specific Israel junction condition for your perturbation. So hence that particular combination. So what does this mean? Well, let's actually sort of construct our Green's function and then look at what happens if we put a particle on the brane. So in general, our Green's function for this spin 2 mode So what we have, when we pull all this together, this is something that looks like your standard massless type of propagator. So this is our massless mode. Here we've got the massive modes. But notice that whereas with Kaluza-Klein theory, if we compactify on a given radius and we look at e to the I mu, e to the I mu z, then we only pick up sort of multiples of our compactification scale. Notice here we've got a continuum. We're integrating all the way down to m equals 0. So you might think actually that's a problem. But if I restrict, well, the other thing you might think there's a problem is if I look at what its source is on the right-hand side, I've got a t over 3. So there's two worrying things here. Number one is the continuum, and number two is the t over 3. So I'll deal with number 2 first. But notice that all I'm computing here is H transverse trace free. And my perturbation is actually a composition of H transverse trace free and F. So my F piece, you can see, is also dependent on the trace. So if I try and put that together, I've got d squared f is minus 8 pi g t on 6. So when I put things together, so when I put everything together, so this is my H, here the first part of this bit and this bit comes from H transverse trace free. This piece comes from F. So you can see that these combine to give me, this is a standard massless part, so my zero mode has the right structure for linearized Einstein gravity. So I get correct massless linearized Einstein gravity. So I get my standard 2gm on R in my Newtonian potential. The other bit that I could worry about is the fact that I've got a continuum integral. So in order to see what that does, let's look at what happens as m goes to 0. Then as m goes to 0, you get a sort of m on 2k for u squared. And so now you know that this massive propagator has a piece that looks like e to the minus mr on r. And so you simply integrate that up. You can see that you've got a dm here, an m here. In the exponent, it's mr, so you integrate with respect to mr, and it pulls out another 1 over r cubed factor. So corrections, so if I just write htt, it's minus 2gm tg Newton, or sort of gmk, I suppose. So although you've got this whole continuum of massive modes, you find that at very long scales, they conspire. So normally you'd expect a massive mode to have an exponential fall off. But because you've got this continuum nudging right down to m equals 0, they sort of combine together to give you a power law fall off. So this is sort of an example of the scale of the power law fall off is given by the scale of the anti-de Sitter space, but it's, you know, it's sort of a justification that in this toy model, you can actually get something that looks like four-dimensional gravity with specific corrections. But the specific corrections are power law rather than Yukawa-type correction. So, this is sort of justifying at least the principle, the proof of principle of having a warped compactification. Okay, I shall stop there.